Hi all, in this lecture we will prove two very useful concentration inequalities that help us go beyond independent random variables. So this will help us go beyond independent random variables and functions that are just the sum of individual random variables. Okay, so we'll be able to go beyond just summing random variables and controlling the deviations. Okay, these are called Azuma's inequality and McDiarmid's inequality. Azuma's inequality is also called the Azuma-Hofding inequality. So let's dive into the first part, which is to derive Azuma's inequality or the Azuma-Hofding inequality. So Azuma's inequality is essentially a concentration inequality for the sum of random variables xi which are not necessarily independent. Recall that we've already shown how we can control the deviations of a sum of such random variables when each of them is assumed to be independent of the others. We'll assume that all the random variables are centered throughout, that is that they are zero mean. So it's useful to first define a property of these random variables, which is what is called a multiplicative family. So a collection, so random variables x1 through xn are said to constitute a multiplicative family if the following condition holds. Okay, so if for every distinct collection of indices I1 through Ik, where k is at most n, so distinct is useful here, is important here. So think of a bunch of distinct indices I1 through Ik, each index lying between 1 and n. We have that the expected value of the product of the random variables described by these indices, so xi1 into xi2 all the way up to xik is 0. Okay, so you take any k, any subset of random variables from this bag of n random variables, and if you multiply them together and take their expectation, then the expectation is 0. Okay, so this obviously means that each of them individually is 0 mean, okay, as a special case. So this is what it means for a bunch of random variables to form a multiplicative family. Now you may ask, why are multiplicative families reasonable to consider? Do they occur in common settings? So it's not hard to convince yourself that if, of course, each xi is itself independent of the others and 0 mean, then trivially you have a multiplicative family. But this is not really the interesting setting to which Azuma's inequality will apply. So a more non-trivial example of a multiplicative family is what is called a martingale difference sequence. So in order to define this, so let's consider random variables x1 through xn with the following properties. So all of them having finite mean firstly, and let's say expected value of x1 is 0, the first one has 0 expectation. Okay, the second one given the first has 0 expectation. This is as a random variable almost surely. Let's say the third one, so every random variable given the previous random variables has mean 0. Okay, conditional expectation 0. And so on until you reach expected value of xn given the first n minus 1 random variables is 0 almost surely. Okay. So if you have such a structure, such a conditional independence structure, then it's we can easily compute explicitly that the expected value of, let's take any subcollection of k of these n random variables xi1, xi2, this is the product up to xik. Okay, so let's assume also that these are ordered, that is I1 is less than I2 less than Ik. Okay, so if you wanted to evaluate such a the expected value of such a product, here's what you could do. So by the iterated property of the expectation, let's condition inside on all but the first all the first Ik minus 1 random variables. So xi1 up to xik conditioned on x1, x2, x3 all the way up to xik minus 1. Okay, and you can easily see that this inner expectation, so the only random variable in this product xi1 through xik that is not present in the conditioning is this random variable xik, the last one. Everyone else is actually being conditioned inside. Okay, so this is ik minus 1. Okay, and so you get the xi1 product up to xik minus 1, and then you have the what is remaining is xik given the first ik minus 1, and you can easily show by the properties assumed above that this conditional expectation is 0. Okay, so this is equal to 0. Okay, so with this let's move on to Azuma's inequality. Azuma's inequality says the following: if you have a multiplicative family of random variables x1 through xn, with each of them being bounded absolutely by the number ci for every I, then the probability that their sum deviates larger than the positive number t, so I should add here that t greater than 0, is at most e raised to minus t square by 2 sum of I equal to 1 to n ci square. So you essentially get the same type of bound as what Hoeffding's inequality gives you, but for more general families of random variables x1 through xn, namely random variables that need not only be independent, so they can be a more general multiplicative family. And this is a very powerful result because, as we will see, it applies very nicely to general processes, stochastic processes called martingales. Before we do that, let's go ahead and give a very nice and elegant proof of this of Azuma's inequality. So I must mention here that the first time I saw this particular proof, very beautiful proof, was after watching Professor B.V. Rao from the Chennai Mathematical Institute derive this inequality, okay, in a workshop on concentration inequalities. So the basic idea of this proof is as follows: you want to basically make a linear approximation to the exponential function. Okay, in fact an upper bound. Okay, to the function e to the lambda x. Okay, so let me draw a diagram here. So let's say that you have x here and you have the function e to the lambda x for lambda some positive number, and you're interested in bounding this exponential function between the range minus c to c, and you seek a linear upper bound. Okay, so you want to connect these two endpoints with a line which will form our linear upper bound. So how can we get this linear function, which so we want the following property for this linear function: e to the lambda x is upper bounded by this function ax plus b for all x in minus c to c. Okay, so a moment's glance should convince you that the way to solve for this is to equate the values at the endpoint. So e to the minus lambda c equal to minus ac plus b, and e to the lambda c equal to ac plus b. So this gives you a equal to e to the lambda c minus e to the minus lambda c by 2c, and b equal to e to the lambda c plus e to the minus lambda c by 2. We will not really require the a for future use, we will just require the b. So just keep this b in mind. This is how you get a linear approximation to an exponential. Okay, so now let's continue here. Let's continue with our agenda of proving Azuma's inequality. So take any lambda greater than 0. For that, let's evaluate the moment generating function of the sum of xi's. So expected value e to the lambda sum of I equal to 1 to n xi is by definition the expected value. So this is splits as the product of moment generating functions, product of the expected value of the product, sorry. And now let's apply the linear approximation, the linear upper bound to each of these e to the lambda x's. So what that gives you is, because the exponential always has a positive range, one can apply this term by term. So it's the expected value of the product of ai xi plus bi, okay, where ai and bi are customized according to this linear approximation depending on ci for every random variable xi. Okay, so it's the expected value of this product of affine functions. And now you can easily see that when you take when you multiply these affine expressions and take the expectation, because of the multiplicative family property, any terms involving xi will integrate out to 0, and you finally are left with only expected value of the product bi, which is really not an expected value at all, it's just a constant. Okay, so this is by the multiplicative family property. Okay, so there is really no expectation after all in the upper bound, and this becomes the product. Substituting in the b values, you have e raised to minus lambda ci plus e to the lambda ci by 2. Now this in turn, by the power series expansion of the exponential, is just the product 1 plus the second, fourth, sixth terms all cancel out, leaving you with lambda square ci square by 2 factorial, lambda to the 4 ci to the 4 by 4 factorial. The next term, just one last term that I'll write out here, is lambda to the 6 ci to the 6 by 6 factorial, and so on. Okay. Now we can upper bound each of these power series expansions as follows. So lambda square, I leave this term as it is, 2. Okay, so 2 factorial is 2. Now what I'm going to do is basically, so let's look at 4 factorial here. So 4 factorial is 1 into 2 into 3 into 4. I'm going to basically drop the odd numbers there. So 1 and 3 there. So 1 into 2 into 3 into 4 is greater than or equal to 2 into 4. So I'll drop all the odd integers there, and since I'm dropping it in the denominator, I only get an upper bound for the final expression. And since I'm left with 2 and 4, I'll take the 2 common out of the odd numbers, and I'll basically get 2 raised to 2 into 2 factorial. Okay, so what I get is basically lambda raised to 4 ci raised to 4 by 4. That's the 2 2's that have come out, and then I'll basically have 2 factorial. The same thing if I do to the next term, I'll have lambda 6 ci raised to 6. I'll get 3 2's as a product, so that's 8, and then what I'm left with is 3 factorial and so on. So you can see that this is basically equal to nothing but the exponent of lambda square ci square by 2. Okay, so that's the bound. So what we have obtained is that the moment generating function of the sum of all the xi's is at most this quantity, and so it follows that psi of the log moment generating function, if you take logs on both sides, at lambda is bounded by lambda square by 2 into the sum of these ci squares. Okay, and then just apply Chernoff to get the final bound, to get Azuma's tail inequality. Okay, so that's the proof of Azuma's inequality. What it gives you is a tail bound for the sum of a multiplicative family of random variables, a tail deviation bound. Okay. Now, why is it useful? We'll give a glimpse of why it can be used very, very effectively. This is a section called application of Azuma's inequality to martingale concentration. So, okay, so we're going to apply Azuma to come up with what is called martingale concentration, an example of a martingale concentration result. So to define, to set that up, let's first define what a martingale is. So sequence, so in our context here, a sequence of random variables z0, z1, z2 and so on is said to be a martingale if two conditions are satisfied. Firstly, that all of these random variables have finite expectation. The second more critical property is that the expected value of any of them given all the previous ones is equal to the last one, the most recent one, zi. Okay, so expected value of zi plus 1 given all previous random variables up to zi is equal to zi. Okay, so basically in words it means that the expected, so very roughly speaking, the expected future, if you're sitting at time I, the expected future value, which is zi plus 1, is equal to the present given the past. Okay, so or another way to say it is that the expected change of the future compared to what you've seen so far is 0. Okay. It's a very powerful property that arises in many stochastic processes, and so it's of great interest to be able to control deviations or prove concentration inequalities about martingales very often. Okay, so with this definition of a martingale, let's assume, so let's see how Azuma can be applied. So let z0, z1 all the way up to zn be a martingale, meaning that basically the conditional expectation of each of them given the previous members of the sequence is the same as the most recent one. Okay, so this means that, so if you take differences, successive differences, and call them xi, so xi is equal to zi minus 1 for I going from 1 to n. It's easy to show that this is a martingale difference sequence. As described before. Okay, so what's a martingale difference sequence? If you take the conditional expectation of each xi with respect to the previous x's all the way up to xi minus 1, then that conditional expectation is 0. Okay, so that's what it means for the x's to be a martingale difference sequence. Also, so you have the important identity that the sum of all these xi's is precisely the final z minus the initial z. Okay, just by telescoping sums. So let's assume that all these martingale differences xi are bounded by some numbers, okay, for all I. So by Azuma's inequality, what does this give us? If you apply Azuma's inequality to the sum of all these xi's, which are a multiplicative family because they are a martingale difference sequence, we have that the probability that the last term of the stochastic process Zn deviates from the initial value by an amount which is c times root n, roughly c square root 2n log 1 by delta. So this is a rare event. Okay. Happens with probability at most delta. So this is a straightforward application of Azuma's inequality. In fact, something much stronger can be said about the same martingale Zn, about the fluctuations of the same martingale Z0, Z1 all the way up to Zn as a stochastic process by using something called Doomb's inequality. So let me put that down here. So in fact, the same deviation holds, the same deviation bound holds for the quantity which is the largest possible deviation of any of the martingale terms. So max over all I going from 1 to n of Zi minus Z0. Okay, so recall that this is of course lower bounded by Zn minus Z0. In fact, this is sort of like a uniform deviation of all the terms of the martingale Z, Zi, with relative to the initial value Z0. Okay, so via what is called Doomb's inequality. So let's state, so to state Doomb's inequality, it helps to define what is called a submartingale. So recall that a martingale is a bunch of random variables Zi such that essentially expected value of Zi plus 1 given Z0 to Zi turns out to be the same as Zi. Okay. A generalization of this is what is called a submartingale. Which says that the expected value of Zi plus 1, the same term, this conditional expectation is at least Zi. Okay, so for all I. Okay, so this is a generalization of a martingale. The mean, the conditional expectation is at least the current value. So with this we can state what is called the famous Doomb's maximal inequality for submartingales. There are several versions of this inequality, but the one we will state here, which will be useful for us, is the following. So if you have a non-negative submartingale, let's say Z0, Z1, Z2 and so on, and if you have T a positive number, then the probability that the largest Z exceeds T is no more than the expected value of the last element Zn divided by T. Okay. So this is very similar in form to the basic Markov's inequality, except that it is much more powerful in the sense that it applies to the uniform fluctuations or uniform deviations of an n-length stochastic process. Okay. So as long as you can control the right hand side, which is the expected value of the nth term of the nth random variable in the stochastic process, then you can hope to control in a uniform way the deviations of this entire sample path of this martingale. Okay, so just to see how this is useful, if Z0, Z1 and so on is a martingale, so let's take the same setup to which we applied Azuma's inequality, where the Zi's were all a martingale and we got this inequality here. Right. So here all the Zi's were assumed to be a martingale sequence. Then what we can do is we can subtract firstly Z0 from each of these. So Zi minus Z0 as I ranges from 0, 1, 2 and so on is also a martingale. Okay, one can easily check this. And now what we can do is we can apply the function e raised to lambda times to each of these martingale elements. So let's consider e raised to lambda into zi minus z0 over all I. This turns out to be a, so firstly this is non-negative, it's a non-negative stochastic process obviously, and it actually turns out to be a sub-martingale. Okay, you can easily check this. I'll leave this to you to check the reason for this property. But roughly, I mean, the abstract reason for this is if you apply any convex function to a martingale, then you show that the resulting sequence is a submartingale. Okay, so hence by Doobe's inequality, we now have a non-negative submartingale here, and we can say that the probability that the largest deviation zi minus z0 exceeds t for any lambda greater than 0. This is equal to the probability. So let's exponentiate both sides. Largest of I of e raised to lambda zi minus z0 greater than equal to e raised to lambda t. And by Doobe's inequality, you get the bound. You can just substitute the expected value of the last element and divide by e raised to lambda t. Okay, and now is where so now we've just reduced this supremum, this max over I equal to 1 to n. So just a single zn minus z0, whose moment generating function we can already control thanks to Azuma's inequality. So thanks to Azuma, the MGF, the moment generating function on the RHS, the right hand side, is bounded. Okay, and we finally get the bound. Probability that the largest deviation of any zi from its initial value is at most e raised to minus t square by 2n c square. Okay, for any martingale process z0, z1 and so on with bounded increments. Okay, so zi minus 1 is at most 3 for all I. Okay, so it's important to note that this bound is obtained, the right hand side bound is obtained by basically applying Doobe's inequality first to get to the last term, the Zn term, the moment generating function of Zn minus Z0, and then applying Azuma's inequality to be able to control the moment generating function of Zn minus Z0, which is essentially its log moment generating function is here, to essentially give a sub-Gaussian type tail here, and then applying the Chernoff bound later. Okay, so that's what this entire technique is. Okay, so the sub-Gaussian, appropriate sub-Gaussian nature of the tail is what Azuma's inequality brings out, and in conjunction with Doobe's inequality, this helps you control uniformly the deviations of a martingale along its entire sample path. Okay, so we come to the second part of this lecture, which in which we will show a very powerful inequality called McDiarmid's inequality that will for the first time allow us to control functions other than the sum of independent random variables. Okay, so this will allow us to see for the first time how we can control something beyond the sum of independent random variables. So maybe more complicated functions of a bunch of independent quantities. So before we present McDiarmid's inequality and derive it, let's define something called a bounded differences function. So a function, so let f be a function from any space Sn, so the Cartesian product of any set S. So this set S can be very abstract. Okay, so any set, n copies of that set to R. So a function f of this form is set to satisfy the bounded differences property. So let's call it BDP. With constants C, so with a constant vector, let's call it C under bar, denoted as C1 up to Cn. So these are C real numbers, these are n real numbers. If the following property holds, so take the function, evaluate the function at any n tuple x1 through xn. So I'll split it as x1 through xi minus 1 followed by xi followed by xi plus 1 all the way up to xn, and take its difference from the same argument except where one argument is replaced, the ith argument is replaced. So x1 through xi minus 1, and then instead of xi, let's say we put a different argument xi prime, and then the remaining arguments are the same. So whenever you have a change of one argument, then the function value deviation is no more than Ci. So this holds for all choices of xi and the different choice xi prime, and for I being in 1 to n. Okay, so roughly, so in words, changing a single argument xi of f doesn't change the function by more than plus Ci or plus minus Ci in either direction. Okay, so this is what is called a bounded differences function. It's relatively stable to small perturbations of its arguments. And another way to express, an equivalent way to express the same property is as follows. So this is an equivalent interpretation of the BDP, of the bounded differences property. The more geometric interpretation. So let's consider a rescaled version of what is called the Hamming distance between 2 points, 2 vectors x and y in Sn. Okay, so the way, so think of a distance or a metric between discrepancy measure between x and y defined as dcxy. C is the vector of coefficients C1 through Cn of the bounded differences property. So let this be defined as the sum over all I of Ci times the indicator that xi is not equal to yi. Okay, so if the Ci's are all 1, you get the usual, what is called the usual Hamming distance between two n tuples, but this is for general Ci. So then the following statements are equivalent. F satisfies the bounded differences property with constants C1 through Cn denoted by C bar if and only if for all x and y in Sn the modulus of fx, the absolute value of fx minus fy is at most d C bar xy. Okay, now to lead us familiar with the analysis and topology, this will remind you of what is called Lipschitz continuity. So another way to say the same thing is that f from Sn to R is one Lipschitz continuous because there is essentially a 1 here multiplying the right hand side. On Sn with respect to the metric, quote unquote metric or distance induced by C bar. Okay. So with this, we are ready to state what is called McDiarmid's inequality, which is a very powerful inequality that applies to the fluctuations of bounded difference functions of independent random variables. So the setup is that if we have a function f that satisfies a bounded difference property and you apply f to a bunch of independent random variables x1 through xn, then the probability that z deviates from its expected value by a number more than t, so t is positive here. So the probability that z deviates from its own expected value by a number larger than t is at most e raised to minus t square by 2 times the L2 norm of the vector c the whole square. This is again an exponential concentration, a sub-Gaussian concentration type result, but for random variables z that can depend on a pretty complicated way on independent random variables x1 through xn. Okay, and in some sense this is a version of this is one instantiation of Talleyrand's principle that we pointed out in the first lecture. Okay, which says that a stable function which depends only in a stable sense on its constituent random variables should essentially exhibit a strong concentration to its mean. Okay, so similarly you can apply the same to minus f and you get a property of the other tail, the left hand side tail of f of z with the same sub-Gaussian type tail decay, okay, of probability. So in the last part of this lecture we will basically prove McDiarmid's inequality, and at the heart of it we will exploit the bounded differences property of f or the stability property of f. So to prove McDiarmid's inequality we will appeal to what is commonly called the martingale method in probability. And at the heart of this method is basically constructing an appropriate martingale given a bunch of random variables to which you can apply powerful results about martingales and their deviations. So in this case, let's do the following. Let yi, so take the expected value of z, which is f of x1 through xn, conditioned on the first I of these x's, okay, and call it so I greater than equal to 0, and call it yi. Okay, for notational purposes we will often refer to the collection x1 through xi as x subscript 1 superscript I, or also in some cases just as x superscript I, okay, where the subscript if not present is assumed to be 1. Okay, so yi is essentially the conditional expectation of z based on increasing collections of random variables x1 up to xi as I ranges from 0 up to n. And the nice thing about this set of random variables y is that it forms a martingale. So this is easy to show offline. So the set of variables yi form a martingale. Okay, this is a rather nice property that emerges just by this definition. So let's now compute. So if the moment you have yi as a martingale, one may be tempted to try to understand its differences, and if they are bounded appropriately, one can probably then go ahead and apply a nice inequality like Azuma's inequality for bounded difference, for martingales with bounded differences, bounded increments. Okay, so to that end, let's investigate. So we have. So let's consider the difference yi minus 1. Okay, Now let's think of this as a random variable. So of course all the random variables y depend on the basic random variables in this probability space, which are the x1 through xn. So let's think of this difference yi minus 1 as a function of the basic values of all the random variables, which is x1 through xn. Okay, in particular we know that yi is going to be a function of x1 through xi. Yi minus 1 is going to be a function only of the first I minus 1 random variable. So in general this difference is going to be a function of the first I of these random variables. Okay, and in our notation this is just x superscript I. Okay, just for our reference. So this by definition is the expected value of z, which is f of all the x's. So let's just say z given big Xi is equal to the configuration small xi minus expected value of z given the first I random variables take the values, specific values small x superscript I minus 1. Okay, so we are trying to express the difference yi minus 1 in terms of the values, the outcome x1 through xi. So let's write this out in some detail. What I'm going to have here is I'm going to write each one of these terms using the basic conditional expectation formula. So let's do this. So the first term is what happens when we try to compute the conditional expectation of z given by fixing the values of the first I random variables xi. Okay, so let's assume that all these random variables have densities. The calculation is the same in a more general case, but this just illustrates the structure of the problem. So one would have integrated f, z is basically f of the first I being fixed to x superscript I, and there are the remaining random variables which we will call x tilde I plus 1 all the way to n. Okay, and we have to integrate this over all the x tilde I plus 1 to n. Okay, with respect to the conditional distribution of the x given this configuration small xi. So what I mean by that is one has to multiply this by the conditional distribution where the first I random variables are fixed to xi, the remaining are allowed to range in the x tildes, and to normalize, one has to normalize to express this conditioning event. This is just p of xi. Okay, p of xi is shorthand for the probability that the first I random variables in the x's assume the configuration small xi. Okay, so this is exactly this integral. In a similar spirit, we can write down the second integral. So this the integration is performed over all random variables other than the first I minus 1. That means x tilde I going to n, f xi minus 1, x tilde I n, and then you have finally a p x superscript I minus 1, x tilde I to n, and one has to divide by p of x superscript I minus 1. Okay, so these are both of these conditional expectations written in detail as integrals. Okay, now let's observe that this term here, okay, so this term here, imagine that xi, so this term has xi tilde. Okay, so the immediate next element after x superscript I minus 1 is xi tilde, and if you were to replace that xi tilde with xi, okay, which is this particular xi here, then we know by the boundary differences property that the function cannot change by more than ci. So this value automatically turns out to have the lower bound. So if I replaced xi tilde with xi, with any other xi for instance, and let all the other arguments remain the same, x tilde I plus 1 to n, then you would not deviate by a number more than Ci. Okay, so this is by the bounded differences property on coordinate I. So applying this bound here gives you that this is at most the same integral x tilde I plus 1 n so let me just write ditto the same integral here minus integral over the same domain. So I can replace this term here with f xi x so the xi gets absorbed in the x superscript I minus 1 and becomes x superscript I, x tilde I plus 1 up to n, followed by the usual xi minus 1 xi tilde n divided by pxi minus 1. And the minus ci just gives you a plus ci at the end just as a constant, because everything else, so if you integrate this term, okay, over the x tilde I n, x tilde subscript I superscript n, you will just get 1 by definition of the conditional expectation of the conditional distribution. Okay, so you have some integral minus some other integral plus ci as a upper bound. Okay, now let's operate on the first term. So to do that, I will put back the first term here. Let me copy and paste this integral here. Okay, so this was the exact first integral verbatim. Now what we have here is that, so let's make two observations here. Firstly, in this right hand side integral, let's complete our right hand side integral. So if you look at the second integral here, this term does not depend on xi tilde at all. Okay, the only dependence on xi tilde is here. Okay, so it follows that if you integrate, you can drop the integral with respect to xi tilde. You can just integrate from xi tilde xi plus 1 tilde onwards, and you can essentially drop that variable here because you integrate it out. Okay, so what I mean by that is that you can just put I plus 1 here. Okay, that's what marginalizing out the xi tilde has got us. Okay, and now it's time to compare both of these two expressions. So we have the same domain of integration. Finally, we have the same first argument. Okay, and what about the second argument? We can write this as, so let's look at this term here, this fraction. So this, by the independence of the x's, recall that we assume that x1 through xn are independent, one can always write this as p of xi minus 1 through xi minus 1, and the remaining x tilde I plus 1 to n multiplied by pxi. Okay, so I am singling out pxi because of the product structure, using the independence of the xi's, divided by, I will again single out pxi from the denominator. Okay, and so this p of xi cancels, and we now have the same term as this here. Okay, so it basically means that the first two integrals are equal, and so you get that this expression is exactly equal to 0 plus ci, which is ci. So what we have shown is that almost surely for any realization yi minus 1 has the absolute bound Ci. Okay. So yi is a martingale whose differences enjoy the ith difference enjoys the bound Ci. Okay, and that's all we need to complete the argument. So invoking Azuma's inequality, for the multiplicative family which is given by the differences of the yi's, we have for t greater than 0 probability that I equal to 1 yi minus 1 exceeding t, which is just the same in the z language as probability z minus expected z exceeding t, is bounded by e raised to minus t square by 2 norm c2 square, which is essentially e raised to minus t square by 2 summation of I ci square. And that completes the proof of McDiarmid's inequality. Thank you.